what are the theorems of moment of inertia? Let us see the theorems of moment of inertia. So, to see why do we need these theorems? Now, if we observe closely the moment of inertia that we found out in the previous lecture for different shape of the body, namely the rod, ring, disc, all of them we found out about the centroidal axis. Now, what if the moment of inertia is asked about some other axis, or let us say the ring is rotating about a tangent to it, or the disc is rotating about an axis which is at one end of the rod. So, axis, how it is present with respect to the body, accordingly the moment of inertia would change. The basic reason is moment of inertia is mass times square of its distance from the axis of rotation, which clearly says it is the axis which is very important, and as the axis changes, moment of inertia of the same body will also change. So, now let us see in this lecture how to find moment of inertia about any other axis if we know the moment of inertia about the centroidal axis. So, the theorems of moment of inertia, there are two theorems which we possibly have. One is called perpendicular axis theorem. This is perpendicular axis theorem, and there is one more which is called as parallel axis theorem. Now, why do we have only two axis theorems? Yes. Now, the axis about which we are trying to find the moment of inertia, it may be perpendicular to the known axis or it may be parallel to the known axis, and because of this reason we have two axes. Now, let us see one by one what exactly it means. First, let me take the perpendicular axis theorem. So, if we see perpendicular axis theorem, the name only suggests, the name suggests that this axis is perpendicular to the known axis. How exactly? Let us visualize this. I am taking one body. Let us say I am taking one body like this. This is the central axis. Now, in this case, what we are trying to do is we have to take two axes which are mutually perpendicular to each other. So, let us say this central axis I am labeling as z axis. Now, I will take two axes which are contained in the plane of body and they are perpendicular to each other. So, let us say one is x, the other is y. This is what we have. Now, let us say now we have to find out moment of inertia about ix, iy. They are the axes which are contained in the plane of the body. So, let us consider one particle or at point P, the coordinates. So, mass of particle, let this be small m, and position, let this be x comma y, the coordinates we can say. Now, if we clearly observe how exactly we can find out this moment of inertia. So, if we clearly redraw it once again, it becomes something like this. So, we have taken this as x and this as y. So, the point is here P. Now, from the z axis is this. Now, from the axis of rotation, if I want to measure the distance, then this is r. So, now if we observe, r square will be what? X square plus y square, because the coordinate of the point P is x comma y. Therefore, from the z axis its distance can be said as r square, which is x square plus y square, and r is root of x square plus y square. Now, this particle will have moment of inertia about x axis. What will be the moment of inertia? So, moment of inertia of the particle can be said as about z axis. So, now mi moment of inertia about z axis is mass of the particle times square of its distance from the axis of rotation, that is r square. So, therefore, what we can say, Iz is equal to m r square is x square plus y square. This is what we have. So, this can be said as m times x square plus m times y square. This is what we have for now the particle m. Now, for the entire body, for the whole body, Iz will be sigma of m into x square, sigma of m into y square. So, what we will get? This is nothing but Iy, this is nothing but Ix. So, this gives us Iz is equal to Ix plus Iy. This is our perpendicular axis theorem. So, what it states? It states that the moment of inertia of a body about an axis perpendicular to its plane is equal to the sum of the moment of inertia of the body about two axes which are perpendicular to each other, but contained in the plane of the body. Keep this in mind. It is not at all essential that x and y are in the plane of the body. In the numericals, they might give you x and z are coplanar, they are in the same plane, therefore y will be perpendicular. Then you have to take Iy as Ix plus Iz. So, please read the question properly and then only decide how to write the equation for perpendicular axis theorem. It is not at all universal to say that Iz has to be always Ix plus Iy. Absolutely wrong. It all depends upon which axes are labeled as in the plane of the body, which one is perpendicular to the plane of the body. It is the moment of inertia about an axis perpendicular to the plane of body is equal to sum of the moment of inertia about the axis contained in the plane of the body. The statement goes like that. That is exactly what the moment of inertia about an axis perpendicular to the plane of body represents. Now, let us see what parallel axis theorem has to say. The name only suggests parallel axis theorem. This means using this theorem we are able to find moment of inertia about an axis which is parallel to the known axis, that is the centroidal axis. Let us see how exactly to proceed in this case. So, here also let us take one lamina, any shape of the body, and the central axis as usual. Let us say this is the central axis. Now, we are trying to find the moment of inertia about an axis, this one, which is at a distance of d units from the central axis, known axis. This is exactly what we have to find. Now, in order to find this, let us consider one particle again P. So, let mass of particle be small m and the position let it be x comma y. This is what we are taking. How exactly? Please observe how exactly to represent this. So, here I am redrawing the same situation and with all the coordinates. This is it, this is it, this distance is d. Now, the point is here P. So, what we can say? Let us say this is x and this is y. Now, we have two triangles. We have to evaluate these two triangles. First, by seeing the diagram, what we can say is x square. If the point is P, if I say this is A and this is B. Now, PA square is equal to x square plus y square, and also PB square we can say it is y square plus x plus d whole square. So, therefore, we can write PB square as y square plus x square plus d square plus 2 times xd by expanding whole square. This is what we get. Now, PA square is x square plus y square. Now, how exactly to proceed? So, therefore, what we can say now? Now, moment of inertia of the particle about the axis passing through A. What we get? We can say moment of inertia about passing through A. Let us say it is this one, is mass times square of its distance from the axis, that is PA square. So, mass times PA square is x square plus y square. Now, MI, moment of inertia of the particle about the axis passing through B. Passing through B, what we get? IB is mass times PB square. So, this is nothing but mass times x square plus y square plus d square plus 2xd. This can be written as m times x square plus y square plus m times d square plus m times 2xd. We can write it this way. Now, this is IB for the particle. Therefore, total moment of inertia of the whole body about the axis through B. What we can say? I. This is sigma of m times x square plus y square plus sigma of m times d square plus sigma of m times 2xd. This is what we can say. Now, this is nothing but x square plus y square. So, what we have? Central axis is C. So, sigma of m times x square plus y square, this is nothing but moment of inertia about the axis passing through A. This is what we have seen, sigma of m into x square plus y square. Similarly, here d is a constant, therefore, sigma of m d square will give us total mass m times d square, where sigma of m is nothing but the total mass of the body. Now, what exactly happens with this third term? So, if I say 2 is a constant, d is a constant, so sigma will happen with only m into x. Observe carefully, every particle which is on, if I take B as the central axis, it is which is at a distance of c, the coordinate of P you have taken from A x y, and from B it is x plus d into y. With A, if you take A as the center, then the coordinate of point P will become x comma y. If you take B as the central axis, then the coordinate of point P will become x plus d comma y. So, if let us assume that our central axis is passing through A, this is our central axis, then x comma y is the coordinate of P, then exactly opposite on the right side of the axis, there can be a point P dash and its x coordinate is negative, y coordinate will be positive only, x coordinate is negative, then in that case sigma of m into x will become what? It will become 0. So, based on this logic, what we can say is sigma of mx tends to 0, because x coordinate is the coordinate of a point on either side of the central axis. So, one side if it is positive, the other side has to be negative, therefore, sigma mx becomes 0. Therefore, moment of inertia about B is moment of inertia about A plus mass times d square. This is the statement for mathematical statement of parallel axis theorem. To summarize, what we can say is moment of inertia of a body about an axis is equal to moment of inertia of the body about the central axis plus mass times square of the distance between the two axes. This is what we can state. So, central axis plus it is the sum of two terms, one is moment of inertia about the central axis and the other term is total mass of the body times square of the distance from the axis of rotation. That is exactly how we can use parallel axis theorem. Now, how to use this equation, these two theorems, the most important aspect, how to use these two equations. Let us apply this equation in some cases and try to understand how to use it. First I am taking, say, moment of inertia of a rod about an axis at the end of the rod. That is to say, let us understand this diagrammatically. There is one rod. Now, about an axis this way, this is how it is rotating, and the length of rod is L, mass of rod is m. This is the axis of rotation. So, in this case, what is to be done? Now, we know how to find moment of inertia I about this axis. So, see, if you clearly observe this, let us say this is a rod, the given rod. Now, the axis is this one. Now, moment of inertia about the central axis is known to us. This is the central axis. So, therefore, applying from what we can say from, observe the two axes are parallel to each other, hence we will use parallel axis theorem. always try to find what is the orientation of the known axis with respect to the given axis. If it is parallel, use parallel axis theorem. If it is perpendicular, use perpendicular axis theorem. So, in this case we have parallel axis theorem. From parallel axis theorem, what we can say? Moment of inertia about the given known axis is central axis. So, moment of inertia about an axis which is asked I is equal to moment of inertia about the central axis plus mass times square of the distance. This is from parallel axis theorem. Now, what is the moment of inertia about the central axis? That we have already derived, ml square by 12 plus m times distance between the two is nothing but L by 2 whole square. So, what we get? Simplify this equation, that gives us ml square by 12 plus ml square by 4, and that is nothing but m L square by 3. This is the moment of inertia about an axis which passes through one end of the rod. This is how we can find out. Now, let us try one more. Let us say we are asked to find moment of inertia of a ring. I am taking, first case I am taking in a ring about a diameter. Let us try to find about a diameter, first case. Now, we have a ring. Let us say the ring is of radius r. Central axis is this, and what is asked? Find the moment of inertia about a diameter. So, now this is central axis and diameter. How the diameter is oriented with respect to the central axis? We see that the central axis is perpendicular to the plane of the ring. So, it is perpendicular to the diameter. So, since central axis is perpendicular to diameter, so from perpendicular axis theorem, what we can say? Just write the perpendicular axis theorem. I z is equal to I x plus I y. X and y are what? X and y are again diameter here. So, I can write, therefore, in our case here I x equal to I y is equal to I about a diameter. Therefore, I z is equal to 2 times I diameter, and I z is what? M r square is 2 times I diameter. Therefore, moment of inertia about a diameter is m r square by 2. This is how we can use perpendicular axis theorem to find out moment of inertia of a ring about a diameter. Care has to be taken that when you apply perpendicular axis theorem, it is not that simply see that the axes are perpendicular. They must pass through the same point also. All the three perpendicular axes must intersect, coincide at one point, then only the perpendicular axis theorem can be found out, because if you have taken Ix, Iy, Iz or x, y, z are mutually perpendicular axes, then definitely they should meet at one point which would be taken as the origin. So, if we take them perpendicular but not meeting at the point, we cannot apply perpendicular axis theorem in that situation. That situation I am taking here, like say for example, the second case I am taking for a ring, that is moment of inertia, this was about a diameter. Now, about a tangent, this I am taking about a tangent perpendicular to the plane of the ring. This is what it says. So, how exactly does the figure look like? See, let us draw one ring, circular ring. Now, it says it is perpendicular to the plane of ring. If you observe it this way, let us say this is the ring is in my hand, it is in one plane. Now tangent is this way. This tangent is perpendicular to the plane of the ring. So how exactly we have to visualize this in three-dimensional form? This is how it is. So if you can observe, the central axis passes like this. This is the central axis and this is the tangent. Therefore, how the two axes are oriented? The two axes are mutually parallel to each other. That is what we can see. So here we have to use. So let me draw the tangent. It is this way and the central axis is also this way. So what we can say, from parallel axis theorem, what we can write? Moment of inertia about an axis is moment of inertia about the central axis plus mass times square of the distance. Now here moment of inertia about the central axis for a ring is mr square plus m. Again distance between them is also r. So that is 2mr square. This is moment of inertia about the given tangent which is perpendicular to the plane of the ring. So that we have to visualize what exactly the axes are oriented. Then only what happens is application of these theorems becomes very easy. Let us take one more case. In this, we are trying to find moment of inertia about an axis, which can be said here the previous case about a tangent. So about a tangent in the plane of the disc. Let us see this ring, in the plane of the ring. It can be disc also, absolutely no problem. The concept is going to remain the same, only the moment of inertia about the central axis changes. So how is it? This ring I have in hand, tangent is parallel to the plane. So the tangent is this way. Now please understand this. This is a very important case. Moment of inertia about the central axis is this, and the axis about which we are finding is this. It appears that they are mutually perpendicular. Definitely not. If you are thinking you can apply perpendicular theorem, please rethink. This is not passing through the center of the ring. The two axes are not coincident, so we cannot use. Then what is to be done? Closely observe this. This ring and this tangent, is there any axis which will make it parallel? Yes. If I use the diameter as the reference axis, then the moment of inertia about the diameter, this diameter and this axis, they are mutually parallel. So what we have to do is, in this case, we have to first take parallel axis theorem, not perpendicular axis theorem. So what we can say, from parallel axis theorem, moment of inertia about the tangent is moment of inertia about the center plus mass times square of the distance. So this center is nothing but moment of inertia about a diameter. So therefore I can be written as, about a diameter we have already seen, it is mr square by 2 plus m. What is the distance between the two? Again radius only. So this we get as 3 by 2 mr square. Please observe how the moment of inertia of a ring is continuously changing depending on the axis about which you are finding. Same way we can find for any geometrical figure of the object. If for the disc also we can find out. So how exactly we are to apply? We have seen in parallel axis theorem and perpendicular axis theorem. You need to find out how the axes are oriented, then only you can proceed. It is not that difficult to apply the parallel axis or perpendicular axis theorem. Only thing is, we need to visualize the orientation of the axis about which we have to find and how it is related to the known axis. That will make calculation more simple. Let me take on the similar lines moment of inertia for a disc. Now I am taking moment of inertia of a disc. Now we know the moment of inertia of a disk about central axis, about the central axis is m r square by 2. Now let us try to find first case about the diameter of the disk. So the axis is the diameter. Now diameter and the central axis, how are they oriented? They are perpendicular to each other. Therefore, what we can say from perpendicular axis theorem, we can say Iz is equal to Ix plus Iy. Here we can say Ix is equal to Iy, and that is nothing but I about the diameter. So therefore, Iz is equal to 2 times I diameter. So therefore, I diameter will be Iz by 2. Now how much is Iz? Iz is mr square by 2, because Iz z axis is the central axis. Therefore, I about a diameter comes out as mr square by 4. See how we can use the axis theorems to find out moment of inertia of a disk as well. Same way, suppose the second case I take about a tangent. Again here two tangents are possible. About a tangent perpendicular to the plane of the disk. So again perpendicular to the plane of disk. Again here disk is this way, tangent is this way, the tangent is this way. So parallel axis theorem. So what we can say from parallel axis theorem, what we can say, I about the axis is equal to I naught plus mass times square of the distance. This is what we have. So here what we can say, I is equal to I naught, central axis is m r square by 2 plus m, distance is r square. Therefore, I comes out as 3 by 2 mr square. This is exactly how we can find out moment of inertia about the given tangent which is perpendicular to the plane of disk. Now suppose that the moment of inertia about a tangent, let us take the third case about a tangent in the plane of the disk, in the plane of the disk. Now if it is in the plane of the disk, then again we have to use parallel axis theorem. So from parallel axis theorem, as we did in case of ring, so from parallel axis theorem, what we can say, I is equal to I naught plus mass times square of the distance. So here I naught is what? I naught is nothing but central axis, that is diameter. The diameter is acting as I naught here. And how much is it? M r square by 4 plus m times square of the distance. So this is 5 by 4 m r square. This is the moment of inertia of a disk about a tangent contained in the plane of the disk. That is exactly how we can use parallel axis theorem and perpendicular axis theorem for finding moment of inertia about any axis which is oriented in a certain way with respect to the central axis.